Hello everyone. Thanks for listening to the lecture. So this is a pre-recorded video. It was intended for September 28th, lecture 8 for EE224. So today I will try to review the midterm 1 questions and answers, and I'm going to upload the annotated midterm 1 solution later also. After that, we will start chapter 5 on inverter, right? Today we will only have a qualitative understanding on the inverter. As a reminder, this week I hope that you can watch both of the pre-recorded videos, and then on Friday, September 28th, we're going to have a makeup session just for question and answer. And I'm going to record the class also in case you cannot come. The midterm 1 is graded already, and you can drop by my office to get your paper. I'm traveling from Monday to Wednesday, so you can come starting on Thursday. If not, I will bring it to the class on October 1st. Okay, article of the day. So today I saw this news. Samsung said that they plan to cut the memory production, and earlier this year they think that the memory growth will be like for DRAM is about 20%, NAND flash is about 30%, but now they expect that actually I was wrong. Earlier this year they think that the DRAM growth is about 20% and NAND is about 40%. But now they adjust it so that actually becomes lower. So it looks like there is a slowdown in the industry, right? Hopefully it won't be a big deal. And on the right shows the focus, right, of the revenue in different IC segment. It would be good to understand what each of these are, like DRAM, specific purpose logic, right, NAND flash. In general, they are dropping, but some of them are actually increasing. For example, wireless communication IC. Okay. So the industry is very dynamic, right? But for us, we just make sure that we understand the theory, right? And it will be useful whether it's at high or low time. So in the last lecture, it was the review for the midterm, right? We review chapter 1 to 4. I'm not going to repeat here because we reviewed for the whole lecture already. But now I want to talk about the midterm. The midterm is finished, and the mean is 49. It is lower than what I expected. And as I mentioned in the announcement, I'm thinking of a way to see how we can really reflect your knowledge. I feel that maybe the midterm is too much. You guys all were under pressure, right? That's why the mean is lower than expected. And after all, midterm 1 constitute only 15% of your total score, right? So don't be too frustrated. And if we have some way to do a makeup, for example, have another test related to chapter 1 to 4, I think that should not affect your final grade too much, right? So we will discuss more in October. And please try to look at the midterm 1 solution and the annotated solution. The most important thing is make sure that you do understand the concepts, right? And if you have any question, email me or drop by or make an appointment. Now let's go to the midterm 1 test. The first one is the Elmore delayed exercise, basically, right? And here shows the circuit that we have. So I was playing with this earlier and forgot to erase it. Now, for this circuit, actually it looks complicated, but the most important thing is that you have to stick to the rule of Elmore delay, right? It asks a few things. First, what is the delay from the voltage source to node 5, right? To node 5, from V in to node 5. So we with this, many people do it right? So all you need to do, remember, the goal is to just add all the RC constants. But how to add it? We have to add it by just putting all the C there, right? C1, C2, C3, C4, C5, C6, C7, right? We have 7 capacitors. And then we find the resistor that is shared between node 5 and the other node. So first we find the path from the input to the output. The path is here, right? From the input through this resistor, this one, all the way to node 5. And then for example, for C1, then we say which resistor share the path as C1, right? And you see that it is this one. From here to here is for V in to node 1. So C1 and C5, they share R1. So we put R1 here. Similarly, what is that for C2? For C2 is from here to here, right? So again, similarly, they share R1 plus R2. Okay? So we do the same thing for every one of them. And eventually you come up with this equation. And the tricky one maybe is for C7. C7 goes from here to here. So for this path, C7 only share R1 with R5. Okay? And that's why you have this term, right? And similarly for C6. Okay? So pretty straightforward. The only thing that you must bear in mind is that you have to find the shared resistance in their paths. Okay. Now, so many people did this question well, but then they got stuck when they go to the next question, asking about what is the shared path, what is the delay from V1 to node 1. Okay. So from V1 to node 1, here you see that the path is just from, so let me go to another figure that would be easier to see, right? So our goal is to ask what is the delay from V in to node 1, right? You cannot just say it is R1 C1. Still, we need to follow the rule. The rule says that list out all the capacitor. So you still need to say C2, C3, all the way to C7. And then find out the shear resistance between these two paths. Right? The first path is from V in to node 1, right? Then how about the path from V in to node 2? It is here. So what is the shear resistor? R1, right? Only R1 is shear. How about for C3? What is the shear resistor? Again, it is only R1, right? So similarly, even for C7, it only share R1 with C7 or with C1. So as a result, the delay from V into V1 is just equal to this one. Delay from V into V1 is equal to this one because they all only share R1, right? This is the only shared resistance. Okay. Now, the next question is, what is the time constant from 1 to 7? This, now you have to bear in mind that the source starts from 1. Now this is the starting point. And the end point is 7. So I don't care about anything beyond, right? So I will just look at this path, right? And then I will start doing the same thing again, right? This is, here I was talking about V in to V1, right? Or I should say V into node 1, right? And then now let me look at node 1 to node 7, right? So for node 1 to node 7, I already drawn the path, and then now we follow the same rule again. Just go through all capacitors, sum over all capacitors, right? C1, C2, all the way to C7, and then we find the shear path, okay? So from 1 to 7, it is this path I just mentioned. Then how about from 1 to 2? There's nothing sharing, right? If you just look at C2, right? C2 is this path. It only has R2. But for from 1 to 7, there's no, the resistor are only R6 and R7. As a result, this is 0, right? And similarly for C1, how about for C3? C3 is this path, right? From 1 to 3. And again, there's no resistor sharing with from path 1 to 7. As a result, this is 0, right? And eventually you see that only C6 has a shear resistor. C6 has a shear resistor with C7, which is R6, right? And then for C7 itself, it is R6 plus R7. So as a result, the Elmore delay constant is C6 R6 plus C7 R6 plus R7. And this is what we got here. Okay, so this is a little bit tricky, right? But the rule is the same, right? I won't go to the second part, the D parts. D parts basically ask you what is the time constant from V in to node 7, right? And you just use the same method, right? And eventually you find that the delay from V in to node 7 is equal to this is V in to node 7 is equal to that from V in to 1 plus 1 to 7. Okay, and that's what I'm looking for. Okay, now let's go to the second question. This one is not difficult if you can see that this is just a transistor, right? So this circuit is called source follower. The goal is that if I increase the V in, I hope that the V out will increase also. But there is a difference between them. V out is not exactly the same as V in. Okay, so what it tells us is that there is no channeling modulation. So it means in your equation, you don't need to include this term. Okay, and not 0 equal to 1, right? Another thing is that there is no short channel effect. So what does it mean? It means VD set is larger than VGT and also larger than VDS. Okay? So we only need to consider VGT and VDS, right? But what is VDS? Since the drain is at VDD, right? So VGT or VG minus VT is always smaller than VDD, right? Because the VG cannot be larger than VDD, right? So from this, I know that I can use saturation equation, okay? And if you can simplify the unified model or just directly use the regular long channel model, then you know that ID equal to this. What is ID? ID is just equal to I0. So some people are confused when they see this current source. This current source has no effect except that it just makes sure the ID through the transistor is always equals to the I0, which is 35 microampere. So if you can see this, then this is just a transistor that has current equal to 35 ampere, right? So we just substitute everything to here. First, VG is equal to VI. This is VG, right? VS is equal to Vout. And then this is VT, right? And then we rearrange equation, and by definition, level shift is Vi minus V0. This means the difference between the input voltage and the output voltage. And you see that this is just equal to this one. And now you see why it is a source follower. Because the Vin minus Vout is a constant from this equation, almost a constant if we neglect the body effect. So if the Vin go up, then the Vout will go up also. Okay. Now, the second part is that what if we negate the body effect, right? If we negate the body effect, then the level shift is just that we just substitute the Vt of V0 by the regular Vt, which is 0.4543, right? Then you get level shift equal to 0.798. And then the third part is say, what is the change of Vt when we take body effect into account? Now, here what you need to understand is that the body, although it is not mentioned here, but I think I mentioned during the exam, is connected to ground. Okay, VB is at 0 volts. But what is Vs? Right? Vs is the source, so it is at Vout. So it means that if the Vout change, the threshold voltage will change. And since the level shift depends on the threshold voltage, right? So the level shift will change also, right? So the goal here is to calculate the threshold voltage at different Vout. And of course, when Vout is equal to 0, right, we know VBS equal to 0. It means that I have an input voltage such that the Vout equal to 0, right? So the Vt doesn't change. It's just the regular Vt, 0.43 volt. But let's say the Vin is so high, making the Vout equal to 1.5 volts, then the Vt will be changed just by use the regular body effect equation, right? And it is 0.7 volts. And then you can just plot this graph. When Vout equal to 0, right, you have 0.43. And when Vout equal to 1.5, you have 0.7. Okay? And this is not a straight line. It is kind of like square root, right? This is due to this effect of the square root here, right? But I still give you full point even you put a straight line. Okay? Now you know the Vt, how it changed with body effect. Now then, let's look at this, right? We'll look at A again. The level shift depends on what? The Vt, the threshold voltage. But threshold voltage change with the outputs, right? So when output equal to 0, the difference between Vin and Vout is related to the 0.43 threshold voltage, right? But when Vout equal to 1.5 volts, threshold voltage becomes what? 0.7, right? So actually the difference, level shift, Vin minus Vout, because this term is constant. So the change of level shift is just equal to the change of the voltage, threshold voltage, I mean, right? As a result, the error is just equal to Vt with no body effect minus Vt with body effect, so it's 0.71 volts. Okay. I definitely think that this is not difficult for you, but because it's so new, many of you got lost, especially you did not realize that this current source is nothing but just make sure the current through the MOSFET is a constant. Okay. For question 3, I also kind of mentioned in the review, and also we have question in assignment 2, right? The goal here is that I have biased the transistor here in subthreshold region, right? And you are going to discharge the capacitor. The initial voltage is 2 volts. And we want to change it to 1 volt by discharging it through the NMOS. Although it's subthreshold, but it is not an ideal switch. So as you can see in this graph, right, it does conduct current when the VG is smaller than VT, although it is very small, very low, the current. Right? The point is that it can be very complicated if the current depends on the voltage at the drain. And as a result, some of you try to do RC delay modeling, right? But however, in this case, we can make it simple. First of all, the current through a transistor in subthreshold region, it depends exponentially on VGS. It also depends exponentially on VDS. But I picked the VDS such that it is so large. So this term is like 1 volt, in the order of 1 volt divided by 0.025. And then you take exponential. So this is much, much larger than 1. So I can, this is much larger than 1, but the negative value is going to be much, much smaller than 1. Right? So I can ignore this term. As a result, what does it mean? This becomes this. And for a given VG, it's just a constant. So this is no different from a current source, which you saw in the assignment, right? The only thing you need to do is to find out what the current source is, right? So it says that at 0.2 volt, you just look at this. Realize that some of you still don't know how to read the log scale well. Okay, let me just explain a little bit. In a log scale port, you have this interval. Each interval is actually 1 decade of difference. 10 to the power minus 11 times 10, 10 to the power minus 10, times 10, 10 to the power minus 9, times 10, 10 to the power 9. So it is 10 times larger in each big interval. And then within the interval, you need to count it. The first 9 is 1. Second 9 is 2. Third 9 is 3. If you keep counting it, eventually the last one is 10. So this is talking about 10 to the power, 1 times 10 to the power minus 11, 2 times 10 to the power minus what? 11, minus 11, right? 3 times 10 to the power minus 11. 10 times 10 to the power minus 11 for the last 9, which is also what? 10 to the power minus 10. Okay, please make sure you understand this. This is very important. Okay, so for the blue 9, what is the current? Firstly, I see here, this is 10 to the power minus 9. This is 2 times 10 to the power minus 9. 3, 4, 5. That's why I claim that for blue 9, it is 5 times 10 to the power minus 9. For the green 9, I start from here. This is 10 to the power minus 8, 2, 3, right? So it is 3 times 10 to the power minus 8. Of course, the units are ampere, right? So that's how you find out the constant current, right? And with the constant current, now I know that current is this. Then I just use the regular equation. T equal to delta Q over I. I need to change it from 2 volts to 1 volt. C is constant, right? But delta V is not constant. V is not constant. So delta V is 1 volt. Then you get this. Here I have a typo. This one should be 0.033 millisecond. Okay? Now let me go to the last question. This question indeed is not easy. But I still try to give score if you sketch something giving the right direction. Right? So the largest hint here is just saying that no need to calculate the capacitance. Assume all capacitance have similar size, right? So that means that it means when you're discharging them, they take the similar time. My purpose is just to tell you that no need to do any calculation. So let's try to understand what's going on here. I'm going to make the screen smaller. So again, this one can make you confused if you have not seen this before. But whenever you see this question, just like the second one, treat it as a transistor and then start putting the voltage to it. Now VG is 2.5 volt. VD is 2.5 volts. Vs is 2.5 volts. These are given. An important thing is D and S are floating. Floating means they're connected to capacitor. They are not connected to a voltage source. So it means if I can discharge them, the voltage will change. Right? But first of all, let's just look at this. VGS equal to 2.5 minus 2.5, which is 0. From here, we know what? This is off. But to be safer, I want to look at VDS also. Sometimes VD may be at even lower voltage, right? It's also, not VDS, VGD, right? VGD, equal 2.5 plus 2 minus 2.52. So this is off. That's why at the beginning, the transistor is at off state. It's not conducting, right? So it's not conducting. What does it mean? It means you have this circuit. Right, so try to draw the equivalent circuit. There's no transistor in between. You see, transistor is off. So this constant current source is going to discharge the capacitor of these two guys. It will keep discharging, right? And this is what? This is the source voltage. How about the drain? It cannot discharge. The drain is here. It is floating, right? This is the drain. So that's why you see the drain is constant. And this is going down, the source. Good, right? So here I give 5 points, 5 points. Will this continue? It will continue until a point when Vs is so low that now it is at 1.8 volts. What happened at 1.8 volts? At 1.8 volts, now the transistor is what? Transistor will turn on, right? Now the transistor is turned on. This is not a resistor, right? This is not a resistor. Now it is a resistor. Then what will happen? Well, besides discharging these two source capacitor, it will start discharging the drain capacitor also. So that's why the drain will go down. Then you may have a question. How about Vs? I think Vs should go down also, right? Because I'm also discharging, right? I don't want to go too deep. If you write down the current equation, you will find that Vs is almost a constant. It will go down a little bit, but won't be too much. The reason is that you have a constant current source here. So the current going through the resistor will be at a similar magnitude, order of magnitude as this constant current source. If this Vs goes down too much, VGS here, VGS minus, sorry, I should say VG minus Vs. Vg is constant, right? Vs, if goes down too much, then the current will go up too much. Then you will see that it doesn't match. So here I want to say Vg minus Vs almost equal to constant. So you have a similar current. Okay? So Vd will keep dropping until what? Until it has the similar potential as Vs. Right? So here it is at saturation. Right? But once it has the similar voltage as Vs, right? Why it becomes linear? Why? Because at this point, Vd almost equal to Vs, right? And then Vgs almost equal to Vds, right? So both of them are turned on. So they will all go down together, right? So here I give 5 points, here 5 points, here I give 10 points, because for each line, right? Finally, this is very, very tricky. No one is able to answer this. And to be frank, when I first tried this example, I was not able to get this point also. That's why I think it might be too difficult for the limited time you have. The last one is so-called diode turn on. So you keep reducing the source and drain voltage, right? Eventually, what will happen? The source and the drain voltage will go below 0. But don't forget that body is always connected at 0 volt. And this is an NMOS. And let's look at this again. This is N, P. Your body is connected to 0. But eventually this becomes, let's say, negative 0.7 volt. Right? Because the source and drain keep going down. They were 2.5, now become negative 0.7. This is a what? What kind of bias? Forward or reverse? Right? This is a forward bias. Okay? So now we forward bias the PN junction, right? We forward bias it. So as a result, all this the current, the constant current, the current source, right, 10 microampere comes from forward diode. Right? Once you are in the forward stage, you will just keep drawing the current from the diode. It's no longer trying to discharge the CGS CSB, right? This one is approximately equal to VBE on. Okay. So in summary, this is a little bit difficult, but on the other hand, when you see this problem, you need to come down and then think about it as a transistor. Try to assign the different terminal with the correct voltage, draw the equivalent circuit, and then think what will happen step by step. Okay, so that's all I have for midterm. If you feel that you still don't understand, feel free to send me an email or come to the office where I will make sure that you understand. Okay. So with this, now let's go to today's lecture, the CMOS inverter. So now we are in chapter 5. We are going to do some more serious stuff, but we will spend 4 classes on inverter because this is very important. Once you understand the inverter, then you will be able to apply the same concept for other combinatorial logic. Okay? So this is the simplest CMOS circuit, but is the most important one, right? The basic one is the most important. Okay, so we need to do a few things. First, static behavior. Static behavior is also so-called steady state, right? We don't think about time. We don't think about when it gets to equilibrium, what will happen. This is usually the VTC, right? The voltage transfer characteristic. Another is the robustness. How is its noise margin? We learned about this in chapter 1, right? Now we really want to apply to a realistic circuit, right? And as before, remember we say PPAC are important. The first P is power, performance. The second P is the power consumption, right? And also area, right? And sizing. This is important also. We don't only look at a single inverter. We are going to look at a train of inverter. How are you going to size your inverter so that you have the fastest speed, smallest area, right? So that's lowest cost, right? This C is for cost, if you forget, right? And this cost, again, related to the reliability, right? So this robustness is also a kind of reliability, right? So always bear this in mind: power, performance, area, cost, and reliability. Okay, so now we learn how to design a best inverter with well-balanced PPCA or PPAC. Okay, let's start. I think you all know about inverter well, right? Inverter, let's just go as a CMOS inverter. We did that in assignment 1. Right, when the input is high, is low. Let's say the input is low. Start with 0. Let's say the input is low, right? The output will be high, right? When the input is high, the output will be low, right? And the good thing is that they will touch the rails. These are called the rails, right? From VDD to ground. Okay, so this is not difficult, but usually we will put a CL here. What is CL? It's the low capacitance, right? But we don't deliberately put a low capacitor there usually, right? It comes from a few things, right? First, it can be the drain to gate capacitance. No. Yeah, sorry. I mean the drain to body capacitance for both transistors. Right. It also includes actually the drain. I mean the, here should be, sorry, DB, drain to body. Also the drain to gate or gate to drain capacitance, CGD2. What else? Of course, it has the wire capacitance. That's what we learned in chapter 4, remember? Right. And also it's used to drive the next stage. So it includes the gate capacitance, or let's just make it simple. We just say the input capacitance of next stage. Right. We lump it together so that it can help us to analyze it easily, right? So this is kind of, we call it lump RC. And you see the problem immediately. We learned in chapter 4, in some cases you cannot do that, especially for the wire. You might need to use distributor model. Okay. On the right, this is a regular layout for a CMOS inverter, right? And here, this is the gate. The poly here is the gate, the input, right? Here is the source of the PMOS. This is the drain of PMOS. This is the source of NMOS. This is the drain of the NMOS, right? And then the source is connected to ground, right? The source of the PMOS connected to VDD, and then the input goes to the poly, which is the gate. This is the gate, right? And then this is the output. That's how you make the inverter usually. And we also know that for an inverter, you can use this simplified model, right? I input a circuit, so now, I input a signal. Can you guess what is the V in here? The output, the PMOS is open, right? What can make PMOS open? That's only when V in is low, let's say 0 volt, right? Sorry, I mean V in is high. I'm wrong. VDD, right? So that the NMOS will be open. Why? Because VGS equal to V in minus 0. This is S is at ground, right? So this is also EDD, larger VDD, larger than VT. That's why this is on. So we model the NMOS as a resistor. PMOS will be off, right? As a result, what is the output? This one will get discharged, so this is 0 volt, right? So V out low is what? 0 volt. Yeah. On the other hand, for this circuit, when V in is 0 volt, now the NMOS is off and the PMOS is on. Right? If you forget, again, what is VGS equal to 0 minus VDD equal to minus VDD, right? And VTP usually is smaller than 0, and this one will make sure this is on. Right? For example, this is negative 2 volt. This might be negative 0.5 volts, right? So VGS is smaller than VTP, or the absolute value of VGS is larger than the absolute value of VTP. Okay? And what is the output here? This one will keep charging until the output is 5 volts, or sorry, I mean VDD, right? So VOH is VDD. So this is for a CMOS inverter. The VOH and VOL equals to the rails, which is very good, right? How about VM, VIL, and VIH? That will be difficult. We need to solve the equations, okay? That's our goal today. Okay. Another thing is about this transient response, right? Based on what we have learned, using this simple model, what is the TPLH? First of all, TPLH means that it goes from low to high, from VOL to VOH, and VOL is 0 volts, VOH is VDD, right? Another more important thing is you have to remember the definition. We always talk about 50%. So, for example, if I have an input, right, going from low to high, then what will happen to my output? The output, of course, will go from high to low, right? It will go from high, oh, this is not what I want, to low. But it takes time. It won't change immediately, right? And by definition, we say that we will find the point at which it reaches 50% of the goal, right? So the propagation delay will be equal to 0.69 RP times CL. And from low to high, the propagation delay will be from 0.69 Rn, for high to low, CL. Right? This is for this one. So any questions? Okay, you cannot. Let me know if you have questions. So characteristic of CMOS inverter, right? First, you can see that because the VOH and VOL are at rails, it has very high noise margin, right? This one will bring it all the way to ground. This one will bring it all the way to VDD. Noise margin will be high. Okay. Another thing is that at steady state, this one is always at 0, and it is connected to the ground through a relatively low resistive path. Why this is important? Because if there's a noise coming in, bringing this to, let's say, 0.1 volt, when the noise is gone, it will discharge, right? And go back to 0 volt. If this is not connected to the ground through this relatively small resistive path, then you will stay at 0.1 volts. And later, if there's another noise come in, it will keep accumulating. So it's not going to self-healing, right? So that's why this make it very robust. Okay? And by the way, what is a typical resistance of a MOSFET? You can just tell people it's about 1 kilo ohm. Why? Because usually VDD is in the order of 1 volt. And when you turn on the transistor, usually the I is in the order of 1 milliamp, right? So this one is about 1 kilo ohm. So it's about 1 kilo ohm to 10 kilo ohm range. Depends on the driving capability, right? But it won't be mega ohm. It won't be 10 ohm, right? This is the same for all technology nodes since maybe 20 years ago, okay? Another important thing about CMOS inverter is what? 0 gate current. Good. Unlike bipolar transistor, you have base current. This has 0 gate current. And also, once it is in steady state, you just look at these two figures. This is off. This is off. There's no connection between VDD and ground, which make VDD to ground leakage 0. In ideal case, we will talk about this in the last lecture of this inverter session, right? Indeed, you have standby current leakage, but it is much lower than other type of logic. Okay, so this thing is simple, but you really need to engrave into your brain. You know immediately that the noise margin is high because it's rail to rail swing. Okay. Now let's try to start working on this by looking at the transfer characteristic, right? You need to solve the equation. But before that, let's do a very instructive and educational approach called the low line plot. How can I construct the VTC, or how do I understand the characteristic of an inverter by just looking at the IV, which is also the characteristics of the individual transistors? Okay. For NMOS, this is easy, right? You are very familiar with this. For NMOS, this is VDS, this is ID, right? At different drain volt gate bias, you have different curve, right? For NMOS, you have high VGS, you have higher curve. Here is the linear region. Right, and here is the saturation region. Can be due to pinch off saturation or velocity saturation of the carrier. And how about this one? The one on the left is PMOS, right? It's nothing special. It just got flipped because of the convention, right? For VDS, it has to be negative because always remember for PMOS, the source is the source of hole. So hole comes from higher potential. So the source is always connected to the higher potential. For drain, for NMOS, source is the source of electron. It comes from lower potential, right? So as a result, in an inverter, right, or in the configuration that we are interested in, the source usually has higher potential. So VDS is going to be negative. If you make the VDS more negative, means the difference between the source, for example, this is 5 volts. Maybe I use another 2.5 volts. And this is 1 volt. Then this difference, VDS equal to 1 minus 2.5, which is negative 1.5 volts. Yeah, here, this point. So you have this curve also. And similarly for VGS, because S is always at VDD, right? Your VG can only be lower. So for example, if VGS equal to 0 volts, then, VG equal to 0 volts, then VGS equal to 0 minus 2.5 volts equals to negative 2.5 volts. And this is this curve. And currents for ID, by definition, this ID means IDS. The current is going down, but we're talking about IDS, so it's negative, right? So that's it for PMOS and NMOS. Now the question is, given these two curves, these two characteristics, are you able to reconstruct the VTC, to predict the VTC of this inverter? So that's what we are going to do. They are in one single circuit. So we try to put it into 2 unit variable, which is V in, V out, okay? And also the H3 variable. This is what? IDSN. This is negative IDSP, right? Because IDS means going up, as I just said. So when you go down, then it is negative, right? But we know that this is continuous. It's a steady state. So IDSN have to be the same as negative IDSP. Okay? So now my goal is to convert the PMOS. Remember this one, the PMOS, IDVD, this shape, like this one, to a scale the same as, or the same axis as the N. Okay, so what I'm going to do is this. Now, this is IDP, right? So if I convert to IDN, then it has to be negative. So you see this one? I put in negative, then it is flipped to the top. Here is IDP. This is IDN. So I'm saying that IDP, originally, it was talking about going up like here. Here is going up, right? But now I try to make it negative, it becomes going down. It's just saying that this current in PMOS, for example, this point in PMOS equals to this point in NMOS. The current. Okay? This one originally, I should put VGSP equal to negative 2.5 volts for this curve. Because this is indeed from VGSP equal to negative 2.5 volts. But I want to change the scale. What is the case when VGSP equal to negative 2.5 volts? It means that VG minus Vs equal to negative 2.5 volt. But Vs is at VDD, right? Which is 2.5 volts, right? Which means Vg equal to 0 volt. But what is Vg? This is Vg. It is equals to V in. So V in equal to 0 volt. So we just put the V in here because later we want to unite it with the NMOS. So that's why now we just call this curve V in equal to 0. It is exactly the same as VGSP equal to negative 2.5. So try this. Similarly, for V in equal to 1.5 is exactly the same as VGSP equal to negative 1. Okay, so I do this flipping and relabel the curve. And now I still keeping this x-axis as VDSP, right? But I want to change it to V out so that I can share the common value as the NMOS, okay? So how is VDSP related to V out? V out is what? It's just the VDP, the drain voltage. Yeah? But VDSP is nothing but just VDP minus VSP. And what is VSP? This is S, right? This is VSP, the source of the PMOS, which is VDD. VDP minus VDD. And that's why you get this equation, right? Because this is, again, VDP equal to V out minus VDD, right? So you get V out equal to VDD plus VDSP. They are equivalent. There's no magic here. We just change variable. And because if I want to plot this one as V out, so I need to do transformation, just shift it to the right. Now, you see that I have a plot which is plotting for IDN as the y-axis and V out as the x-axis. But this is again for PMOS. It's just telling me that how the PMOS current is going to be related to the V out at different bias condition. Okay? Think about that. You can pause the video and think about that. It is not that difficult, but it's pretty messy. The main point is that you need to understand where VG is connected to, right? Although here it can be confusing. VG is directly connected to Vin. Source VSP connected to VDD. All these things, think about that. The goal is that I transform this ID VD curve on the left lower corner to the equivalent ID VD curve, but with the label that can be shared with the NMOS, where the x-axis is V out, and then the current is the drain current of the NMOS. And with this, I can overlay them together. Remember this is a little bit busy, but this set of curve, this one, this one, this one, this one, this one, these are from NMOS. And these are from PMOS. From here, where we just did on this upper right curve, we overlay them together. So now they have they are the solution of separate transistor. But if they are put in the inverter, the V out has to be the same, right? And as I said, this one is just IDN. It has to be IDN. So they are the same, right? And also they need to have the same V in. So the solution is the one that satisfies both curves. Solution is the one satisfy both curves. Okay, so for example, let's look at this point. This is the point which is V in equal to 1.5 volts for NMOS, and also V in equal to 1.5 volts for PMOS. The V in has to be the same because they are connected together. And at this point, I have the same current and also the same V out. So this is the solution, right? By definition, it is solution because it's telling me that when V in equal to 1.5 volts, I have this amount of current and I have this amount of V out. Is this a solution? This one has the same V in, the same current, right? It also have the same V out, but no, it has different V in. Why? This is because this one has V in, it has V in equal to 1 volt for the PMOS, but V in equal to 1.5 volts for the NMOS. You cannot have different V in the inverter. They have to be the same. So this is not the solution. Okay? So with this, I can start constructing the VTC. So I have a V in, I have V out here, and try to look for the solution. The first point is V in equal to 0. Okay, V in equals 0. And what is V out? Well, V out here is 2.5. Good. So I got 1 point. Then later I go to V in equal to 0.5. This is 0.5, this point. And what is V out? It's almost equal to 2.5 too. 2.5, right? Very close. Right? That's good. Then later I reduce the I increase the V into 1 volt. Now it is 1. Let me write that. This is 0.5. And then this is 1. At 1, this is V in equal 1, right? What is V out? V out is here. Remember, V out is the x-axis. It's even lower, but still pretty close to the rail. Okay? And then I don't have solution here because I don't have very dense V in curve. Because once I jump to V equal 1.5, which is this point, V out becomes very small. Right? V out is here. This is the V out. When V in equal to 1.5. And then when I V in go to 2 volts, then it's even smaller. And when V in equal to 0, not 0, 2.5 volts, then V out equals 0. And I will just link them together. And this is my VTC. Okay? This one is not useful nowadays because you have computers, right? But it is very good for you to gain intuition into the VTC or to do a quick estimation of a circuit. Even in the future, you don't have a CMOS, you have a other loading or other special type of circuit. You can do this type of low line plot by converting individual electrical characteristic on and put them on the same scale or same variable or the same axis, and then you will be able to find a common solution. And it will give you a lot of insights. For example, from here, you will see that all these points are concentrated to the left and right. And you jump so suddenly from high voltage to low voltage. It means I have a very steep slope here, very high gain, which is very good. That's what we want, right, for noise margin. So finally, this is the plot in a more accurate scale, right? But the point is this: I want you to understand at different region, what is the status of the transistor, right? So when V in is low in this region, low, right? Let's say it's 0 volt. You know very well this is off. And how about this one? This is actually in linear region. Why? You just try to solve it. You find that this is VDD. Always look at when you want to determine the region, look at the terminal voltage, right? So this is 0, this is VDD, this is VDD, so it is fully on at both drain and source, right? So if NMOS is off, PMOS is in the linear region or resistive region. Resistive means, RES means resistive or linear. Okay. Now when you continue, let me change the color. When you continue to increase the voltage, for example, to 1 volt, now the transistor is barely switched on. It is switched on now, right? It's switched on. And the PMOS is also switched on. But however, this is still around VDD. Still around VDD, the output. So this one is at what voltage? At what condition? VDD is at Vout. The input is still low, right? This is 2.5. Let's say maybe to be more accurate, now it becomes maybe 2.3 volts, right? This is in saturation, right? Because VG, maybe I should write here, VG minus VT equals to about, let's say, 1 volt minus 0.7 volts, almost equal to 0.3 volts. But VD for NMOS, right, equals to 2.3 volts. So as a result, this is at saturation, right? And then later, it will switch. This will keep going down. The Vout will keep going down. And Vin will keep going up. Then the PMOS will enter into saturation also, right? So the most important point to take away in this lecture is when you are switching, both are at saturation. Okay. Okay, so that's all I have for today. Please watch the next lecture.